Okay, so hi, my name is Latavia. This summer I worked with the Biophysical Modeling Group in CCB, where I studied how asters might position themselves in large cells. So in this video, we can see three different sea urchin cells, and the bright spots inside them are asters. We really want to know how these asters move to the middle of these cells. So this is similar to asking if you were like in a very small room, how would you get to the middle of this room? So if you're in like smaller space, you might be able to use your arms to feel around for the room's walls and kind of guide yourself to the center. But if you're in like a pretty large space, your arm just wouldn't be long enough for something like that. So if you have no eyes and your arms are like not long enough to reach the walls, how are you going to get to the center of this room? This is essentially what we're asking of the asters. We want to know how are they moving to the middle of these cells, and this is what I spend my time trying to simulate. So an aster is first made of a centrosome in the middle, and then from the centrosome, we have thousands of microtubules which branch off of it. So microtubules are long polymer chains which can polymerize or depolymerize, meaning they can grow or shrink when they gain or lose a polymer. Then they're also polarized, meaning they have plus ends and minus ends. So the plus end is on like the outer edge of the aster, and then the minus end is like on the inside toward the centrosome. And on top of these microtubules, we have small motors, which can travel up or down the microtubules. Then on top of these motors are they can have cargo that they can kind of transport sometimes. So if the motor travels to the minus end, which is again on the inside, those are dynamo motors, and if they travel towards the plus end on the outside, those are kinesin motors. So if we wanted to simulate how these asters can move, there's a lot of things we need to take into consideration. Two of those things are the fact that first, microtubules are semi-flexible polymers, and second, the movement of the motor and cargo combination on top of the microtubules generates a lot of cytoplasmic flow. So as you can see in the picture, as the motors walk, they kind of push on the microtubules, and that exerts a force in the opposite direction of the way they walk, and that can either stretch or compress the microtubules and kind of cause them to move. So in this image, in this image, we can see the motor moving towards the minus end, and you can see the bottom arrow with the force is kind of stretching the microtubule out. And if it was a kinesin motor, it would be going the opposite way, and it would be causing the microtubule to compress. So now that we know some things we want to model, we can talk about the math methods we'll use to do this. So first, we know the cytoplasm, which is the fluid in the cell. We know it's very viscous, meaning that it's thick. And if you have a thick liquid, you can kind of ignore any inertial forces it may have. And when you ignore the inertial forces, you can use Stokes flow to model this fluid. So first we have mu, which is the viscosity of the cytoplasm. Then we have u, which is the velocity. Then we have p for the pressure. So after we model the cytoplasm, we can move on to the way the microtubules might move. And to do that, we can use Euler-Bernoulli beam theory. So we can find the pressure, or we can find the force that the microtubules exert on the centrosome, using E to be the flexural modulus, which is kind of how bendy the microtubules are. We have x is a vector, s for the arc length, and then t for the tension. Then we can use this force to find the torque on the centrosome. So we have the same variables from before, but we also have r, which is a vector from the center of the centrosome to the outer end where the microtubule attaches to it. And one thing that's kind of important, we kind of assume in these simulations that the microtubules are very long and thin, meaning they have no thickness. So we can kind of treat them as a simple center line. And the force that the motors exert on the center line is found in the motor mobility equation, which isn't shown here. Then
in your notation, the subscript S is derivative with respect to position. So what does X triple S mean?
Yeah, so derivative of the vector with respect to, I think it is position.
Position or time?
I think it's position. But I'll have to check though. I'm not exactly sure.
Okay.
Then we want to model the way the microtubules and the cytoplasm interact. And to do this, we can use the boundary integral method. So we have force per unit length, which is the small f there. And then we can also use Green's function for flow, which is the g down here, where g is like the velocity. So some details about the program we used. So Mike Shilley's team has been developing this for a while. It was first written in Python by Flatiron and Goldberg, and then later rewritten into C++ by Robert. And we also use a parallel hybrid programming method where we use OpenMP and MPI at once. And so the goal, a lot of the things that we use are just to make the code run faster and like have better efficiency, because this does take a lot of computations and a lot of data and things like that. So we really want whatever is best for those type of things. We also have fully resolved fluid dynamics written by Wen and Daria. So after I run a simulation, all the information goes to an output file. Then I can send this output file to peer review where I can visualize the asset moving in the cell. So some details about the simulations. There's a lot of parameters we can play around with. We don't change all the things at once, just because it's easier to like start small, change a few things, and then go from there. So we can change the number of microtubules from the centrosome. I usually kept mine at 500. We can change the length of the microtubules, something that I kind of changed a lot. We can change how bendy the microtubules are, the growth and catastrophe rates, which is like how fast they grow and shrink. I didn't mess around with that. We can change the way they interact with the cell boundary, something I also didn't mess with. We have the geometry of the cell. I kept mine as a sphere with these simulations. We can play with the properties of the motors, so like the force of the motors, and also the type of the motors, meaning like dyno or kinesin. So here's one simulation I have. The smaller video is the zoom out version of the first one. So here I'm using kinesin motors. We started the aster at the cell's periphery. These are, again, 500 microtubules, about 10 microns long, with the force of negative 0.4 piconewtons per micron. And you can see the way it kind of moves to the center. So this took about an hour and a half to run on 24 cores. And we can only see about 10 seconds of the simulation. So that you can tell it kind of took like a little under 10 minutes just to like generate 1 second of this video right here. So that can kind of give you an idea of like how heavy these computations are. So then I have another simulation using dyno motors. These microtubules are a lot longer, about 20 microns with a force of 1 piconewton per micron with, again, 500 microtubules. So you can see we place it near the cell periphery again, but it's not moving towards the center. You can see it's kind of pushing against the cell periphery, making it bend. So this one ran for about 40 minutes, and we can see 60 seconds. It was kind of faster to run, but you can also see it kind of moves a lot less. So then besides motion, we can also look at some other things. So here we have some fluid flow. So you can see like this is an aster with microtubules that are 70 microns long. It's placed at the center. So you can see the fluid flow red towards the centrosome. Fluid is moving a lot faster, and then away from the center is moving a lot slower. So things like this are really important because if we can simulate the fluid flow, we can compare this to what we see in real world experiments. So that can tell us like if they're similar or different, we can say, okay, what mechanism is causing this flow? And we kind of compare that to our simulations. So some things we want to look at in the future, first thing would be dynamic instability, meaning we want to see the microtubules polymerize or depolymerize in the cell. I didn't do, I just kept them at constant length. We want to see how the microtubules might interact with the cell periphery, some pulling and pushing forces that might occur, microtubule nucleation. So as I mentioned right now, microtubules only like stem from the centrosome, but they're also able to like stem like branch out from each other. So we do want to experiment with that later. And we also want to play with the cell geometry. Right now it's just a sphere, but we do want to change this geometry and ask like how might changes the geometry affect aster positioning. And these are just some people I want to thank. So.
Time for questions. Anybody have a question? Carlton?
What kind of fluid are you using?
Use your seat mic, please.
What kind of fluids are you using in your simulation for the fluid dynamics as the aster's position?
So do you mean like the cytoplasm in the cell, or?
Oh yeah, the cytoplasm.
Are there other questions?
Understand how big are these asters relative to the cell? When they swim through the cell, do they affect the cell?
The cells are 100 microns in diameter, and then the asters. So I made my different lengths. So some of them are like 10 microns, some are 20, but they can grow and shrink. So we can make them very long or very short.
So they're smaller then, but not trivial.
Yeah.
Are you thinking about like in the future adding like other things that would normally be in the cytoplasm, like other kind of like obstacles, I guess? Have you guys
Um,
done that, or?
I'm actually not sure. I think if we do, we might start with like adding multiple asters because in the cell there are sometimes multiple asters, like when they pull the chromosomes apart. So I think if we do add anything, that might be like where we start.
Cool, thank you.